As it's well known, each organization has its own dialect of English. That's why there are two probably not too much understandable abbreviations on this slide, SGX and WKM. SGX is a software guard extensions of Intel, and by extension I mean instruction set extension. WKM is an opposite to BKM, or best known methods, and means, of course, worst known methods. Today I'm going to talk about mistakes that can be done, and usually done, with SGX Enclave programming, and going to present a training target for hacking SGX Enclaved software. First of all, let me introduce myself. My name is Michael Atlas. I work in something like 10 years as a security researcher at various places, such as Intel, NDS, and Cisco at Haifa, Israel. Some of you probably know me as W-S at Reverse Engineering Stack Exchange. And I have to state some things loud and clear before we starting. That's, of course, for legal. The opinions expressed in this presentation and on the following slides are solely those of the presenter and not necessarily those of any of the presenter's current, previous, or future employers. This is not, in addition, this is not a SGX advertisement presentation. There are a lot of others better than this one. And I respect the signed NDAs. Please expect I cannot answer this question as an answer for really interesting things. Please note that SGX is a bit complicated, and some of this talk will be dedicated to describing SGX itself and its SDK. There are a lot of good presentations about it, and good people made a lot of presentations for this. In addition, I'll try to avoid spoilers in the details of specific WKM's implementation. So here is an agenda. I'm going to remind you what is down vulnerable approach. I'm going to speak about what is SGX Enclave, how it changes standard threat model, and why I think that it is good. What is platform software, SDK, and what is standard structure of the application with SGX Enclave built with this SDK. The training target itself, its code quality and finding hardware for it. I'll list bad practices, the most important part. I'll do a demo of my training target, and we'll try to discuss tools and better practices if we'll have time for this. Some of you probably remember what is down vulnerable exercises. So down vulnerable something is a something which is down vulnerable. There are a lot of them for iOS application, Android application, Linux, Windows, web application, database server, etc., in almost any alive software ecosystem. It is standard practice to provide legitimate, I'm not a lawyer, check with your lawyer first, training target and dry security environments. In addition, it intended to show damned if you do instead of blessed if you do practices intentionally. So you can imagine the quality of code I'm going to demonstrate. So I made such a thing for SGX Enclave. All this presentation is intended also to provide you a context around its usage. And of course, I call this training target a down vulnerable SGX Enclave according to this old respectable tradition. So, what is SGX Enclave? SGX is new Intel Trusted Execution Environment and instruction set extensions. It contains two opcodes, ENCLE-U and ENCLE-S, with so-called leaves, numbers of which are passed in REX register. It exists in 6th generation of Intel processors, Skylake and Kaby Lake, and later, hopefully. And its main goal, quote, to protect selected code and data from disclosure or modification. The CPU hardened SGX enclaves are protected areas of executions that increase security, even on compromised platforms. SGX enclave is distributed in .dll or .so form, okay? And it is actually a blob of code with well-defined interfaces which can be called from the usual applications as functions. In short, SGX Enclave is an isolated, signed, and attestable piece of code with well-defined interfaces that allows the programmer to execute it safely without the intervention of other parties, even most privileged, such as BIOS, OS, hypervisor, SMM, and management engine. Okay, first question, why is it interesting? First of all, because I like it. In addition, this is the first solution I know about where security anchor code is not privileged, which is definitely the right thing. And I think I reviewed enough SGX enclaves during my work at Intel to be able to make some hopefully representative conclusions about common mistakes. One of the main ideas behind this invention is to reduce the attack surface of the application, which means creating some kind of code and data enclave which cannot be accessed by privileged software, with some additional security properties. If the software is designed properly, the attack surface of the application security anchor is reduced to defined enclave interfaces instead of all privileged software and all the application itself. Privileged code, as I said, cannot access enclave's internal state and other enclaves too. In addition, enclave is signed and attestable, and in addition, SGX Enclave is able to use unique cryptographic keys derived from processor-specific fuses, enclave measurements, and some other things, which means that the same enclave will not be able to decrypt something which was encrypted on other system. This enclave has the following architectural properties. First of all, altered enclave will not load. It is signed loading for altered enclave loading will fail because it's cryptographically protected by the hardware. At all, it's possible to load only debug and whitelisted enclave because there are some parts of platform software that will not allow to load not registered enclave. As I already said, nobody can access its internal state. In addition, a memory encryption engine is used, okay, which means that enclave's memory is encrypted to avoid hardware attack. Evicted memory is also encrypted and protected from replay attack. And, this is very important, enclave has ring tree privileges. There is a usual design pattern. More secure code should be more privileged, and all negative numbered rings in Intel architecture are proof of that. SGX designers made completely different decision. Enclave itself has ring tree privileges, so it allegedly cannot harm anyone else. In addition to this, Enclave is able to prove its authenticity to authorized parties. These properties define some consequences. First of all, SGX Enclave is specially designed for keeping secrets safe, which actually means that SGX Enclave is a perfect place to hide and isolate interesting activity, and you can define word interesting as you like. SGX Enclave can be very small. Smaller SGX Enclave has significantly smaller attack surface, which is obvious. And the most important thing, SGX Enclave is a part of an ordinary application. SGX Enclave is a code written by programmers. They are making mistakes. And I know that my English is bad, but I really mean that they are writing this code just now in this very moment and making mistakes just now, at least in countries where Sunday is a working day. And it is a never-ending process, and it will continue until something will not disappear, SGX or programmers. Having such a thing in the system makes some shifts in standard threat model. SGX Enclave as a feature were designed to allow correct and secure enclave functioning in worst condition, even if the system is completely compromised by the attacker. It is assumed that the attacker already has system-wide capabilities, which is the end point and the ultimate goal of the standard attacks. And it still holds the ground, even in this case. Attacks on enclaves are starting after the most ultimate standard goal of the attacker is achieved. No memory access means actually no debugging. No debugging in offensive context means no smart fuzzing, which means that at least for SGX release enclaves, pure static analysis is back. It also changes the focus of the attack. A really successful attack on SGX enclaves will be mostly focused on extracting of enclave secrets and reusing enclave capabilities rather than code execution, just because, by definition, the hacker already has all the rest. As a part of changes in threat model, timing attacks are getting more and more important, and this is a very special case. But you are more than welcome to explore this direction. It actually works. There are some articles published recently about this. I keep in this long and exact quote from the SGX Enclave Writer's Guide here for those that cannot hear me and will be reading this presentation. Please don't rush into reading it. The essence follows. Here it is. The Intel architecture aims to provide protection, it's quote again, against software side channel attacks at the cache line granularity. The Intel SGX architecture does nothing to improve this position. More important, the application enclave should use an appropriate crypto implementation that is side channel attack resistant inside the enclave if side channel attacks are a concern. Let me translate it from English to understandable. It is on responsibility of the programmer to care about that. New tasks requires new, or you can call it good old set of tools. This brings us to a bit different skill set. Running fuzzer and exclamation mark exploitable in WinDBG is definitely not enough. So the following skills are required for SGX Enclaves reviewing and attacking. First of all, code review, both in source and binary level, which mean old good reverse engineering. It will be much more productive. You'll need to use dump fuzzing, and attacker will also need at least some basic knowledge in cryptography, because AES GCM is used for default data sealing. The following things really make all the situation different. If the enclave is good, it is really small. Smaller enclave means smaller attack surface. But on the other side, the fact of enclave existence reveals the most interesting target and presumably not accessible location of the secrets immediately. All the interesting things are located at the same place in the enclave itself. And you have no debugging capabilities inside for release enclaves. In standard case, the enclave is readable and you literally can read it all. However, enclave itself can be encrypted. But even in this case, the enclave driving application is reverse engineerable and blind fuzzing is still possible. So again, static analysis is back. Seriously, I mean it. So most interesting things will be hidden in the enclave, which makes the enclave the first priority target. Now we know what enclave is and what properties it has. Let's explore what is required for playing with it. First of all, it appears that having processor with SGX support is not enough. By the way, by this specific link, you will see list of all Intel's processors that supports SGX. Lars Richter, in addition, at IX, maintains a list of SGX-enabled software. The link is also here. Okay. This link is very useful because quote, SGX is turned off by default and must be enabled via some specific MSR, model-specific register. Only the BIOS can make changes in this register. For example, Intel SGX SDK requires as follows for the hardware. Okay, required hardware, 6th generation of Intel Core processor on UA-based platform with Intel SGX enabled BIOS support. I spent a week for finding this specific laptop with working SGX. Just try to imagine, you call in a support and to specific hardware vendor and asking the question, does this specific system support SGX on BIOS level? They obviously don't understand the question and trying to clarify it. And they don't ask what is SGX, they ask what is BIOS. But thanks to Dell, okay, I found this computer, it works. In addition to hardware and BIOS, we need some software. Playing with SGX requires SDK and platform software, which is actually out of scope of this talk. So platform software, it's a kind of runtime environment, which contains driver, some architectural enclaves, and service to orchestrate them all. And SDK is for compiling enclaves and enclave driving applications. So here's the definition of the environment. We have possibility to play with enclaves in Windows. Here you have an installation guide link. Here I'm writing a exact revision number of an SDK I worked with. It works in Visual Studio 2013 and 2015. And despite the fact that it is wrote that you need Visual Studio Professional, with my Visual Studio Community Edition 2015, it works fine. In addition, debugger is included for debug mode enclaves. In addition, there is enclave simulation. And you already have seen the requirement that this SDK requires. In Linux, we have almost the same, but the used development environment is Eclipse. It also has some kind of debug script, okay, for debugging SGX Enclave, which is called SGX GDB, and actually the same requirements. Code that cannot interact with user and/or other code is invisible, inaudible, unobservable, cannot do anything, and can be considered as non-existing. So Enclave, as it was said before, should have well-defined interfaces, and here is the way in which these interfaces are defined. EDL file. It looks like that EDL means Enclave Definition Language. The idea behind it is very similar to the COM interfaces definitions. There are some definitions of call inside and outside the enclave. Generally, it has a rich language. There are imports, complex data types, includes, etc., etc., etc. Here, you can see how trusted section is defined. These are calls inside an enclave. And here, you can see untrusted part. In order to perform system calls, for example, the enclave have to leave enclave mode and return to enclave driving applications. Okay, so this EDL file is not compiled directly. There is some utility that generates a code from it in order to push some data inside an enclave and get some data out of it. This is done with a tool called EDGERER, okay, which is part of SDK. Here you can see the link to its documentation. Just a moment. It generates code in C to solve this problem. This code is added automatically into the project in Visual Studio, both enclave and enclave driving application for trusted and untrusted parts correspondingly by Visual Studio SGX plugin. By the way, it's a great tool for building enclave phasing harness once you have or can deduce EDL's file content correctly. Just import your EDL file into the project from the enclave or elsewhere in Visual Studio. We'll see an example closer to the end of this presentation. Let's talk about how these calls are implemented. We have the following parts: user application, untrusted generated code, which is generated by this excellent utility, platform software code, trusted generated code, and enclave code itself. I remind you that these, with colors derived from red, are untrusted part, running in usual hackable mode, and this is trusted part, which is running in enclave mode. Let's try to imagine an eCall call inside an enclave and understand how it works from different code parts perspective. Here is how all transitions between the code parts look like. First of all, the application calls the generated stub. After that, this generated stub packs the data and passes the control to platform software DLLs, which passes us to enclave mode, which arrives to trusted generated code, which unpacks all the arguments and calls enclave functions written by user. Okay, after that, it returns to, after the function ends, it returns to the generated code and makes all the way back, packs all the data, unpacks it in untrusted mode, and returns the control to the user functions. I remind you, all these red-derived things are untrusted. Let's add O call to this picture, call to operating system. It looks a bit more interesting. So when the start is the same, and then enclave wants to call operating system, it does all this process in opposite direction. It calls to the generated stub, the stub generated by EDGERER utility from the enclave, which actually writes the data outside and passes the control to platform software DLLs. And it calls the generated stub to collect the data to the user variables. Then it calls the function that user wrote as a no call, returns back, same way with passing collected data, and then returns back from the enclave. I remind you, this is untrusted. Okay, let's see how exactly it looks in actual code. Just a moment. Where is my code? Where is my code? Here it is. I'm running here a debug enclave, and I stopped on debug breakpoint inside an enclave, and I want to show you all the things inside. This is, by the way, one of the samples of using this EDGERER utility. This function is a user function which user called. This function equal pointer user check, okay, is a stub that was generated by the EDGERER utility. It looks actually this way. It calls platform software function and packs the arguments here. After that, it goes here, and I hope you'll see it. Just a moment. View disassembly. Great. Okay, so you see here assembly command ENCLAVE, which is one of two instruction extensions commands. After that, it uses some kind of library function of SDK, and here is the trusted generated function. Just a moment, sorry. Here is the trusted generated function, which actually collects all the data and calls actual equal of the user. Here is the functions that user wrote. Let's look how it looks like in IDA. Okay, I hope that you see something here. Okay, this is disassembled code of this, but the most interesting thing here, okay, that this platform software function is actually xrefable. You can see all the calls to the enclave, and there is enough information to create EDL file by yourself. In addition, just a moment, no, you can see that each function of this kind, okay, receives a list of OCLs, which also can be easily recovered from enclave driving application. Okay? Just a moment. Okay, now we have seen how it should work. Let's start with overviewing the promised damned vulnerable SGX Enclave. First of all, the link is here. I made this repository public, I think, 2 hours ago. And you can and should build it and debug it as you can and as platform allows. Debugging flag, unfortunately, is a part of the key derivation material, which makes release build much more interesting target. If you want to use this in release environment, you have to sign it with Intel yourself, on behalf of yourself or your organization. Unfortunately, I cannot distribute signed enclave because of licensing issues. Licensing guide actually requires that I will not distribute any kind of software which is deliberately vulnerable, okay, which is actually the case. There are some additional statements I have to state loud and clear, okay. First, all mistakes I deliberately inserted to this DVSE, or damn vulnerable SGX Enclave, were observed in real life in the code which was marked as finished or near to production quality. To my best knowledge, all mistakes I am going to speak about were fixed in original enclaves, but I saw these mistakes enough times to make conclusions that these mistakes are common. Some of these mistakes deliberately are made a bit easier to exploit. Of course, it's only exercise. And it doesn't mean, however, that there are no other mistakes I made not intentionally. In order to write the DVSE, I had to resurrect the bad programmer buried inside of myself since I stopped to work as such. It was very hard. In addition, it was very interesting psychological experience, so you know what quality of code to expect. Just a moment. So, what is this? On what exactly we are training? This is Windows application, and I'm planning to port it on Linux sometimes. It is intentionally vulnerable, partially copylefted from Stack Overflow and samples, and of course, okay, completely not usable in production. I beg you, please don't shoot yourself in the leg. You were warned. So the application consists of client, server, and the evil DRM. The evil DRM includes time-limited video on demand, secure media storage, and secure local library. Secure. You see the quotes. In the real life, this kind of application will be protected with obfuscation, remote attestation, and other tricks and untrusted part. I decided to leave application protection out of scope. Defeating it is not the point. The main goal of this exercise is to create another application that will get all the enclave's secret and will be able to decrypt the movies sealed with the enclave. So, server part, which is actually out of scope of hacking, it gives up all the files if asked correctly, and defeating it is also not the point. So it's very simple Python script that gives all files encrypted via SSL according to configuration. It is SSL server with self-signed certificates, and I checking SHA-1 of the certificate inside the enclave. I added some public domain cartoons as media examples. At least I downloaded these cartoons from the internet site with this claim. So here you can see a general usage instructions. Install all the components, compile the code including the enclave, run server and client on the local machine as wrote in readme.md. In short, use, hack, enjoy. Then the question is, what mistakes are there? Now we're going to explore the promised WKMs, worst known methods, I observed on real-life examples. System programming provides a lot of possibilities to shoot yourself in the leg. SGX Enclave programming is not an exception, and we're going to explore these possibilities just now. So please do not expect too much implementation spoilers ahead, but the general spirit of the things is kept. I divided these WKMs according to the development phase they should be discovered. So design review should avoid surprise, bad design. So where bad design includes no remote attestation, no local attestation, possibility to exclude the enclave from the process, so, which means to connect to the server and to get off the files. And one additional and very important thing, it includes trusting that enclave will not run with other application. Okay, actually, I'll show it during the demo. In addition, it includes bad cryptography, which actually includes key material and AES-GCM IV exhaustion with sealing, not constant time crypto and other sensitive algorithms, and writing crypto code all alone. You can call your crypto PhD, and if you didn't do that, you are probably in problem. Additional things for design. But random. For example, please try to avoid custom number generation. Custom random number generation. I understand the noble idea we can't audit RDRAND instruction and then we'll use it only for random number setting, but after taking this unfortunate decision, the responsibility on this is yours alone. In addition, another problem is trusting the untrusted components. Okay, of course, the attacker can control everything which is passed via OCLs. And of course, using of enclave as confused deputy. Decrypt secret using the hidden key shouldn't be an equal if enclave doesn't check outside environment, which is, to my opinion, is almost impossible to do reliably. Code and build review can review the following thing. Okay, first of all, misconfiguration of the enclave. Actually, I have seen debug enclave which was almost sent to production, which is actually a problem because debug enclaves are debuggable. It can also avoid well-known vulnerabilities such as not checked inputs or buffer overflows because enclave will not make your code secure if it has mistakes inside. There are a lot of examples of it, in a wide range from time of check, time of use on input buffer to not checked inputs and so on. Additional problem which becomes more and more important is leaving secrets unattended, even inside the enclave. Okay? Actually, you can use memset s to clear secret if needed, and please clear secrets as soon as possible after usage if you're running these enclaves. Okay? More things to be caught here. Accessing not secure memory from the enclave because it's controlled by the attacker. Timing attacks because of algorithmic flaws, such as string compare-like checks. Okay, it is direct target for timing attacks. And at all, using secret as a source of conditional expression is always a problem. And one of most interesting things, inventing a wheel instead of using SDK. Please don't implement sealing, multi-threading, cryptography, and other things existing in SDK yourself. Sorry. I had seen some of custom implementations of this idea. None of them made sense, and all of them ended badly. And, of course, fuzzing at the end. It is able to find some of well-known vulnerabilities and accessing non-secure memory from the enclave. Okay? Please note that most of really interesting things almost cannot be found dynamically. During the conference, somebody mentioned bad design guard, so we really need it. Okay, demo. Let's exfiltrate something from the enclave. All the rest you'll have to either find yourself or contact me for the solution or wait until it will be published. Intended vulnerability is not checked index for reading the buffer, which leads to the data exfiltration, okay, which was stored in the enclave for all the enclave lifetime. This vulnerability is easy to find manually, and I'll show it to you. Just a moment. Okay. Here is Visual Studio, where all these things are. Just a moment. Oof, this is a problem. Just a moment, sorry. I'll open here the corresponding files. Okay. Generally speaking, the vulnerability is here. Okay, one of the equals of the enclave, okay, receives the page of EPG or electronic program guide, and receive its page number, okay, which obviously can be negative, positive, and not checks indexes. I understand that this vulnerability is a bit artificial, but I intended to show it here and to show results, how exactly it affects the system. So, actually, here is the problem. You can see it in IDE also, if you want. Let's run and see how exactly all these things work. Okay? First of all, let's run the server. Run. Second of all, let's run the application. Okay, you can see that this application downloaded the EPG and something which is called coupons. It is able to show us what movies exactly do we have. Okay, as you can see, it is cartoons from the public domain. And when we play it, okay, when we play it, it actually was also already downloaded for me. Okay, this is downloaded to the local database folder, encrypted and played and decrypted inside the enclave. Okay. So let's view what exactly do we have in my solution. Okay, I'll have to return it back. Just a moment. This solution actually contains the enclave itself, the UI itself, which we were running, and additional application which I calling enclave test. Okay, in this enclave test, okay, we are loading the same enclave. Okay, we are loading the same enclave here. We actually opening the file for extracted memory and taking some additional pages with negative and positive numbers and dumping it into the file. Let's run it for a moment. Okay, I'm just running it now. And please note all these prints. Okay, these prints actually coming from the OCLs, okay, which I actually changed. Okay, I inserted another OCL implementation. So actually we can see what exactly this enclave is doing. And if we want to see what exactly do we have in this memory, we can see the following. I'm sorry. Okay, here. We see strings extracted from enclave's memory, and these strings are so-called coupons which can give you coins to view another cartoons. In addition, by the way, you can see the certificate details, okay, because which were downloaded from the SSL server. Please note that revealing this vulnerability is really easy, but it illustrates the following WKMs. First of all, leaving secrets unattended, it's thus very bad design. Secrets should be cleared immediately after usage, just for defense in depth, and enclave didn't help us in anything. So bad code inside an enclave is synonym of failure. Here you have a lot of secrets. In addition, it was one of standard vulnerabilities, not checked indexes. This vulnerability probably looks a bit artificial, but I have a really good reason to show in it. Okay, as an example of how small and harmless issue can undermine all the security model, there is a proverb in Russian which means don't put all the eggs in the same basket, with very clear meaning. Don't place all of your valuables at the same place. In the boundaries of this analogy, any kind of secure enclave, and it doesn't matter how exactly it is implemented, is a basket with eggs. Okay? Once you drop it, you break everything. The second thing, that I had seen similar things in real life enclaves. They were a bit more complicated, but it is an exercise after all. And of course, I go in to publish the walkthrough as soon as possible. Let's try to speak a bit about prevention in the field. First of all, static code analysis tools such as Clockwork, okay, are working surprisingly good if applied properly, okay, with every nightly build. Manual review of all possible things gives the best results, but with the results we have a problem, because the review should be conducted by very much qualified people, and it is still a probabilistic process, and something will always be overlooked. As for fuzzing, we have nothing new except of old good and dumb enclave fuzzing. There are no tools that allow us to use something more complicated. The only hope here is that good enclave is small and missing details and information can be obtained by code review. Again, bad design guard to rescue. We definitely need it here. In addition, I think that it is possible to use something related to symbolic execution, and it may be interesting, but I didn't use it myself for this purpose. By the way, Intel opened the bug bounty program. All the platform software is a good target, okay? And I don't know how exactly they pay, but they pay. And all the PSW should be a critical part of the infrastructure, but bugs which are found sooner are easier to cure. okay, what I'm going to do next, where I'm going to continue. I go into porting this down vulnerable SGX Enclave to Linux. I'm going to publish walkthrough and the exploits. I go into write automatic the Python script for automatic deduction of enclave equals and ocals and see how exactly it will succeed. In addition, I'll try to use something like abstract interpretation or symbolic execution for fuzzing. Again, enclave is small, and the most of problems with code path as explosion are less relevant here. There are some useful links here for all those which will read this presentation instead of watching video. Starting link for Intel, good tutorial from hardware point of view, good security analysis, of course, Intel SDM software development manual, okay, the corresponding part, links to Linux SDK, which is interesting, and Enclave Writer's Guide. Okay, special thanks. Thanks to Lars Richter that maintains the list of SGX-enabled hardware. Okay, he helped me a lot. Thank you to my previous colleagues. Okay, if they hear this, it was an honor to work with them, and I wouldn't find all these bugs alone. Okay, part of these colleagues actually wrote these bugs, and another part of these colleagues helped me to find them. And thank you very much, dear RECON organizers. I see presenting here as an honor. So, questions, please.
Hello, thanks for the presentation. I worked with some of this stuff, and you are right. Speaking with the technical support, saying what is a BIOS, they reply that they don't know. But basically, I have not understood completely how works the attestation. I mean, I know that there is like a key to signing the enclave, but how is it organized? I mean,
it's okay. First of all, it's a long story. Write me an email. Okay, you will see my email in the presentation, and I'll reply you with the links to complete documentation. I just don't want to explain it not correctly. It is
yeah,
really...
I know that is a pain like that, the attestation, and I was curious to understand. Like
it's impossible to it's impossible to explain in 3 minutes.
Okay, perfect. Thank you very much.
I was just wondering if you could comment on your interaction with Intel and the process for setting up an NDA. Were you able to interact with them as like a private citizen and sign their NDA? Did you have to work through your company to
actually this presentation passed a legal review, okay, and that's what I had to do. In addition, I don't see any reason why I cannot interact with them after that as a private citizen.
Okay, so basically your company set up the relationship with Intel in order to get access to the SGX development stuff, and then you're able to...
I'm not pretty sure I understand the question.
Basically, can somebody as a private citizen, will Intel even allow them to register for SGX in order to get the SDK and the signing certificates or whatever it takes?
I'm sorry. Okay, first of all, downloading SDK and PSW requires registration only. But if you want to distribute release enclave, you need to sign it with Intel. And I actually didn't even try to do it. And this is related to the question of remote attestation that it was asked about. I think the private person is able to do that. I'm not pretty sure. But write me an email, I'll check it for you.
I think the previous person that asked the question was not aware that you were actually an Intel employee.
Yes, I was Intel employee until a week ago. Yes, sorry for not mentioning that. Now I'm proudly unemployed.
What kind of memory hardening protections are applied by default when building SGX Enclave applications like stack cookies and and executable permissions on memory and things like that?
Let me consult document. Okay, that's exactly the question I can't answer without consulting the documentation.
Okay.
Sorry.
No problem.
So I know that the standard mode that people use when distributing an enclave is open code. Have you seen any instances of people sending down a stub to the enclave, having the enclave attest to the stub, and then sending down encrypted code so that to make an attacker's job more difficult?
Okay, there is one thing I can say. Okay, there is an API in the SDK which means load encrypted enclave. But I never seen examples of this. So at least on the level of API, this possibility exists. So thanks for watching. Feel free to contact me. Okay, here is my email. And sorry for an accent. Thank you for the pleasure.